Hello and welcome back to yet another talk on the NPTEL course on advanced plasticity of solid continua. So, for some time we have been discussing this thermo-visco-plasticity because that is the most important model of practical use. So, we are spending quite a bit of time on that. Today we will be doing something very important based on whatever we have discussed so far, the theoretical aspects. Today we will try and implement this entire thermo-visco-plasticity. A typical implementation we will see how to do within the finite element framework in a computer, right. So, this is how we proceed today, that is in developing the consistent tangent stiffness. That is the most important information for solving the problem, right. So, let us go ahead and do it. So, first let us derive the consistent material tangent that we have been doing because from consistent material tangent we can determine the consistent tangent matrix, right. So, the consistent material tangent, as you know, is basically the derivative of the stress sigma, numerically you have to do, with respect to the strain epsilon, right. So, also recall that in developing this kind of a numerical tool for thermo-visco-plasticity, what we do essentially is to discretize the time axis from starting time t0 to as time moves on, t1, t2 and like that. So, we assume that everything, all the variables have been already solved at time, the last available time, that is at time tn, and our objective is to find these unknowns at the immediately succeeding time t at n plus 1, right, tn plus 1. So, with this in background, let us recall the incremental relations that we need to actually work with at time t n plus 1 with the plastic strain and the hardening variables known at time t n. Define the elastic part of the strain to be equal to the total strain minus the plastic part of the strain minus the thermal part, all sampled at n plus 1, that is at time t n plus 1. Similarly, the elastic law would give you a stress strain relationship, the standard one, that is sigma, that is the stress at time t n plus 1 is the coefficient elasticity tensor, appropriately written either in a fourth order or a second order form depending on the implementation. In a finite element implementation, you know that the fourth order tensor does not really work because it is much more difficult to represent a fourth order tensor in a computer. So, therefore, we represent this sigma and epsilon etc. as vectors, 6 dimensional vectors, so that this script C will be essentially a 6 by 6 matrix, that is a tensor form, a 2 tensor form, right. So, we have this sigma n plus 1 equal to C times epsilon with an appropriate inner product. In this particular case, if it is a vector matrix multiplication, this is a matrix, this is a vector, right. So, in the implementation, the associative plastic update we will have to bother about. So, delta lambda is basically the incremental magnitude of the plastic strain, okay. Np is the flow direction, okay, at time t n plus 1, and so this is the update that we are interested in. So, basically we need to find delta lambda, right, and also remember that the flow direction itself is given by the gradient, that is basically the subdifferential, but assuming that everything is smooth, f is smooth, you can actually take the gradient of f with respect to sigma to get the flow direction np. Otherwise, you have to take the subdifferential. We all know this for associative plasticity. now for the hardening variable, that is also an unknown, we have the following update, right? So that is alpha n plus 1 is alpha n plus, again delta lambda contains all the variables of interest, all the internal variables of interest, times h n plus 1. Okay, remember that this h n plus 1 need not be the same as np n plus 1, right? So this is basically the flow direction pertaining to the evolution of the hardening variables, which is given by the subdifferential of the of the function f, which is the yield function with respect to capital X, that is the forces, the generalized forces associated with the hardening. Okay, remember that this capital X are the generalized forces which are essentially thermodynamically conjugate to alpha dot, producing power. So okay, so the stress in the trial corrector form, that is, first assume a trial stress, call it sigma trial, purely based on elasticity solution, okay, starting with the known solution at time Tn. So the trial is that is the trial stress, sigma trial, which is given here. This is your elasticity tensor times the elastic part of the strain, which is given here. Okay. So this is, again, remember that this is a matrix vector multiplication when you do an implementation in a computer. Now with this sigma trial, we can find the actual sigma n plus 1, write an expression for the actual sigma n plus 1, because sigma trial is the elastic part of this stress. So we remove from it the plastic part. Okay, so basically C times the lambda n times, there is a p missing here, np is the flow direction associated with the plastic strain. Okay, so that is the expression for sigma n plus 1. Now let us form the residual equation. Okay, so let us discretize the Perzyna flow rule. You already know about the Perzyna flow rule in thermo-visco-plasticity. So let us actually the error in that flow rule will be our residual equation. Okay, so the flow rule is basically, in a general form, is of this form. Okay, so where z contains all the rate variables, z dot contains all the rate variables, which are epsilon p dot and alpha dot. The corresponding thermodynamic generalized forces sigma, this capital sigma, consists of small sigma and x, right? So that cap sigma in a product with z dot will give you the total plastic power. Okay, the power. Now introduce the plastic multiplier rate. Basically, this quantity we can call the plastic multiplier rate. You see there is a plus here which we are not putting this. So you remember that this angular bracket with a plus, it is basically the Macaulay bracket. The definition of that you should recall. If you have forgotten any one of these, then please go back and refresh your memory and then come back, so that there is no difficulty for you in understanding the steps. And this is the generalized flow direction. Okay, and this is the multiplier, plastic multiplier lambda dot. Okay, so this is defined here. This plus I am not putting typically here. You assume that the usual definition of Macaulay bracket is valid. That means this quantity is its actual value of f if f is greater than 0, or otherwise it is 0. Okay, so now we can write therefore the same flow rule. This is the flow rule, right? We can write the same thing as in terms of this shorthand, lambda dot times the generalized flow direction, which is the subdifferential of f with respect to cap sigma. Discretizing this implicitly over the time step delta t, that is what we need to do, right? So we can write therefore, instead of z dot I will write delta z. Okay, instead of lambda dot I will write delta lambda. It will have to be divided, you see, because the left hand side was z dot, so only delta z will not be enough. So, we will have to divide by delta t, but that is the same thing we have to do for delta lambda also. So, that will cancel. So, therefore, there is no need to explicitly write delta t here. So, in the incremental form this is true. Okay. So, this is okay. All right. So, now clearly delta lambda is lambda dot at n plus 1 delta t. This is a very interesting point here, because what we are saying is that you could have written delta lambda equal to lambda dot n times delta t, but in that case the unknown would not have come here. Okay. Right. So, your lambda n plus 1 is an unknown, right. Your objective is to find delta lambda by subtracting from lambda n plus 1 lambda n. Lambda n is already known. So, therefore, this is basically an implicit form of writing delta lambda. Okay. So, in terms of this unknown lambda n plus 1. Now, let us proceed to substitute for delta lambda in the expression which was given in the last, which is basically this, right. So, let us substitute that, and what we have is delta lambda is basically again the Macaulay bracket. I am typically missing this plus sign, provided there is no confusion. You understand this is a Macaulay bracket, but recall that this is basically the exponential factor, the rate sensitivity exponent. This eta we should actually call it in terms of mu. This is basically not the entropy, but this is mu, the viscosity. So, if there is no confusion, I will just keep eta, or maybe for your benefit I can put it as mu, but anyway let us continue. Eta is basically here viscosity coefficient. Okay. So, if eta equal to 0, then we have rate independent plasticity. Please stick with this for the time being. Typically we use mu, and eta we use mu for the viscosity coefficient, and eta we use reserve for the entropy, but in this case it is slightly different. Okay. Now so remember that in this delta lambda expression on the right hand side we have written this yield function f as a function implicitly in terms of its arguments at time t n plus 1. So, you see sigma n plus 1 x n plus 1, right, like that. Okay. And theta n plus 1, because this is temperature dependent. So, now bring all the terms to one side for the residual, which is the discretized flow rule, right, which is delta lambda minus the expression for delta lambda in terms of the Macaulay bracket of f, and that should be equal to 0. Correct. This residual ideally should be equal to 0. That is, we need to find these quantities in such a way that the residual becomes 0. So, this scalar equation, because sigma n plus 1 can be written in terms of delta lambda. You remember that sigma n plus 1 is basically there is a delta lambda appearing in the expression for sigma n plus 1. So, you see basically what we have here is that in this sigma n plus 1 and similarly in x n plus 1 there will be delta lambda, right. So, therefore, this is an implicit, because I need to find delta lambda but this is an implicitly written equation for delta lambda. So, we need a nonlinear equation also. So, this is an implicit algebraic equation to find delta lambda. You can use Newton-Raphson and things like that, but then we do not do that. We use Newton-Raphson, but in a systematic way in finite element method, right. So, towards that we find this material tangent, the algorithmic material tangent, which is basically essentially it corresponds to a further linearization of my residual. Okay. So, as before, as always, it is essentially the derivative, the gradient of the stress sigma at n plus 1 in terms of the strain epsilon. Okay. So, this is the sigma c algorithm, that is the consistent material tangent. Now, this I can write. So, let us now write everything, because we need to write everything in terms of delta lambda, that is the unknown for me, right. So, sigma n plus 1 is sigma trial minus this, correct. So, if I actually take a differential point of view for this, because sigma was basically C times epsilon E, right, that is the elastic part of the strain, and elastic part of the strain was written as total strain minus epsilon P, which is basically NP lambda, right, minus so that particular thing. So if you now, so sigma equals this calligraphic C, sorry, vector matrix vector multiplication total epsilon minus epsilon E, right. So minus epsilon P, right, epsilon P, correct, and that actually is lambda NP kind of a thing, right. So basically what you have here, when you actually take d sigma, you have this kind of an expression C d epsilon minus you have to actually instead of epsilon P, if you put lambda epsilon NP, basically in an incremental form you have to write, okay, because your sigma n is known, right. So actually I should have written this as delta sigma equal to C, like that, okay. So delta epsilon minus delta epsilon P and all that. All right. So if you just take the differential on both sides of this expression for sigma, then you get here what you have. So one term you will be getting here differential of delta lambda, and the other term will be differential of NP, the flow direction, okay. So this is the expression for d sigma. Now the differential of the flow rule, if you want, remember that in von Mises plasticity the differential of the flow rule is simplified because dNP is taken as 0, NP is taken as fixed, the direction, but in a more general setting it need not be the case. So therefore if you want to take account for dNP being not equal to 0, then you can actually write this in this way, okay. So this is basically from the expression for NP itself, okay. So you can understand that, right. So essentially so remember that NP is del sigma of F, correct. So from that, okay. So and F is a function of both sigma and X, correct. So from there this follows, all right, you understand, right. So now the next thing is let us proceed. We have basically terms like dx here, d sigma here, in this d sigma appears here, you see that. Similarly let us write an expression for dx. So because x depends on alpha, the corresponding hardening kinematic type variable, so therefore I can write this del x by del alpha d alpha and call del x by del alpha as calligraphic h, which is essentially or script h, whatever. So h d alpha, okay, this script h d alpha, okay. So moreover d alpha we can write in terms of the following expression, that is h d alpha, this is capital H, just okay. So that is and delta lambda dh. Recall that this h here is basically the partial derivative of alpha with respect to lambda, all right. So at this point, to avoid expansive expansions, because there are too many variables and we have allowed for NP to be changing direction, which is a very general case. So let us call this term, this is basically a matrix, or basically in terms, provided you write sigma as a vector in a finite element implementation, this becomes a matrix, right. So let us call them by some name, A, okay, script A, script B is this del square, the cross derivative del square sigma xf, and then we can write dNP in a simpler form like this, right, avoiding all these partial derivatives, they are there included in this A and B. Now, so this is a rather complicated procedure, you know, there are lots of steps. So please follow through with this. After this class you can actually go through it once more carefully. Now this d sigma, therefore, you know, putting all this whatever we have done so far, we can write d sigma as, the first term is very clear, the second term is also standard, the third term it basically had C, what was that? Yeah, this term, right, delta lambda dnp, where dnp we wrote in terms of this A and B, right. So all this come here, okay. So let us arrange them together, because there is a d sigma appearing on the right hand side here too, right. So put everything on the left hand side so that there is a clear separation to solve for d sigma, something like that. So therefore put this on the left hand side. So this is the expression which is containing d sigma, and on the right hand side the rest of the terms, and let us call the coefficient of d sigma as identity plus delta lambda C inner product A, okay. So if you do all this and solve for d sigma, then we basically need to invert M, right, M inverse all this, okay, the right hand side. Now so the residual equation, that is the flow rule, discretized flow rule, you remember that was basically R equal to 0. So the basic idea now is to use everything that we have got, that is d sigma etc., right, in this residual equation in its linearized form, because the residual equation is non-linear, right, in delta lambda. So this is exactly what we do. When we say we take the differential of the residual equation, now this is basically the linearization step in finite element which we use, okay. This is basically linearization of R. So let us do that. This is the linearization, del R by del delta lambda, because R is a function of these three quantities by chain rule, okay. So for active plasticity, that is when actually the plastic flow is on, then F has to be greater than 0, and the expression for the residual, right, will be this, and this is the standard form. So again now I have actually come back to mu. Remember that basically there is a small typo here, I am sorry about that. This mu is the same as the eta earlier, which is basically the viscosity, okay. So I will just make it very clear here because of this typo, okay. Now they are the same thing. So basically this is my expression for R. So F is greater than 0, so basically I do not have to put the bracket here, the Macaulay bracket need not be put on F, you understand, because the Macaulay bracket becomes exactly equal to F if F is greater than 0, right. So that is why it is just F by mu, because F is positive also, greater than 0. Okay, so now let us do these derivatives carefully, because in the linearization of R we need these derivatives etc., okay. Now so first remember that, just observe that del R by del delta lambda is 1, then del R by del sigma you can clearly differentiate, which is here, okay, and del sigma F you put as NP, okay. So and then finally you have del R by del X, which is here, okay. So substituting all of this into the residual variation, you know, this R is 0, but we are not directly dealing with R, but we are dealing with the linearized form of R, okay. So basically we are using this, okay. Then if you substitute all of this into that linearized form of R, then you get this equation, d of delta lambda, which you want to find. Delta lambda is the object, is the quantity to be found, delta t times all that, okay. So now you can, now this d delta lambda is an extra thing. So basically that arises here, you understand here, okay. So this d delta lambda we can actually replace in terms of these quantities. So put that, and then put that d delta lambda in the equation for d sigma which we got. Okay. So then we get this d sigma equals all this, right. Okay. So basically finally we have this expression for d sigma. See, finally our objective is to find d sigma by d epsilon, and in the process we have used the residual, the discretized flow rule and its linearized form. Okay. So this is my expression for d sigma, correct. I need to find still the expression for my tangent, the consistent tangent. So you would recall that in this d sigma, if we, there is a d sigma on the right hand side also. So take it on the left, there is no other d sigma. So you can write everything together on the left as a factor of d sigma, and then on the right hand side we have this, right. Now the important thing is that I need d sigma by d epsilon, and there are other quantities like so dx, right. So basically I need to write dx also in terms of d epsilon. So how do you do that? Because dx can be written as del x by del alpha d alpha, which is basically script h d alpha, okay. And then you use the incremental form of alpha in terms of alpha n plus 1 equal to alpha n plus delta lambda times h to write this d alpha in this manner, right. Now make an approximation, right, because there are too many terms. This term contains two factors, both of which are incremental. This delta lambda is incremental, dh is also incremental. So let us actually neglect the term with dh, so cross it out, okay, only retain this term. So therefore because this term will be a second order term, in that sense this is a first order term in terms of the increment, right. So therefore d alpha is approximately equal to h d delta lambda, and dx therefore I can write as, because this is from the last expression, okay, this is the script h times h d delta lambda, okay. Now here comes the trick. So now you can use the identity, you see, basically d delta lambda you can now write as in terms of d sigma, okay. So g, this is the expression. So therefore we have dx in this form, right. So we can actually solve for dx from here, because we have to take it this side. So dx is basically this, right. So define the scalar quantity here. This is a lot of work. Define the scalar quantity kappa, okay, as this, as shown here. Then basically this is my equation for solving for dx. So basically after some algebra we can write dx basically equal to some matrix like object, right, matrix vector. D sigma is a vector now in the finite element implementation. So this p depends on the hardening moduli, okay. So substituting all this into the expression for d sigma that we already had, we see that dx basically is proportional to d sigma. Basically therefore the hardening force that is coming up is proportional to d sigma up to the first order, okay, in all the increments. And hence since d sigma is proportional to d epsilon, so therefore dx is also proportional to d epsilon ultimately, okay. So if that is the case, then we actually can make use of this fact in this term where actually the dx term appeared, right, okay. So you see that everything here is proportional to essentially d epsilon. In the expression for d sigma, everything is proportional to d epsilon, and we finally therefore can write d sigma is basically some algorithmic tangent material modulus times d epsilon, the vector representation of the matrix epsilon, all right here. So you can therefore write C, this is, I am sorry, this is a mistake, this is C minus, okay, I am sorry about that. So this is the algorithmic tangent stiffness, right, not tangent stiffness, the material tangent, right. Here Q contains contributions from stress and hardening, which is basically given here, okay, and all the other terms are already defined, okay. So NP is the flow direction, etc. C is basically the usual material, you know, the elasticity coefficient matrix. Now, so this is basically for a very general case. What we will be doing now, we will stop this particular lecture here, okay. This is a very general problem that we have tried to solve. The most difficult thing in this exercise of trying to simplify or get into the form in which d sigma by d epsilon can be found, we had the difficulty that NP, the flow direction, was changing. That is why dNP could not be set to 0. But in most practical applications, unless you find it badly necessary for more advanced applications, we typically have the flow direction not changing, okay. The flow direction is more or less fixed. In other words, the changes in the flow direction are weaker than the increments in the other variables of interest. So therefore, what we have to do now, we can simplify this entire algorithm in a much significant manner. For example, if you use the von Mises plasticity, then NP has a fixed direction, so dNP is 0. So in this particular case, we have a simplified expression for the material tangent. We will discuss this in the next lecture, okay. So thank you for your attention. We will meet again soon. Thank you.